Now kernel. Kernel of a linear map, also known as the null space, right, is the part of domain, right, a linear subspace of the domain. This is subspace of the domain which is linear, right, linear subspace, which is mapped to the zero vector of the codomain. So any point in the domain mapped to zero vector of the codomain, then the points all in the domain are called the set kernel, right. So kernel is a mapping points in the domain to the zero vector of the codomain, that is the null space. Integral transform, so it is a transformation that convert the original function f of x into another function f of p by integrating the product of original function f of x and a kernel function. So original function f of x and its kernel k, then f of x into k. So integrating that f of x into k, you will get another function f of p. This is called integral transformation. If k p of x, p comma x is the function of two variable p and x, where p is the parameter independent of x, the function f of p is defined by f of p, which is equal to integral minus infinite to plus infinite k p comma x f of x dx. This is the integral transformation of small f of x, right. It is denoted by t of f of x. Next, Laplace transformation. The Laplace transformation is the integral transformation of a function f of x is defined by L, Laplace transformation. L of f of x is equal to f bar of p, which is equal to integral 0 to infinite e power minus px f of x dx. Here the kernel k p comma x, it is equal to e power minus px, x greater than or equal to 0, 0 x is less than 0, right. So this is a integral transformation with kernel e power minus px for all positive x, then it is a Laplace transformation. The Laplace transformation is exist only if the integral 0 to infinite e power minus px f of x dx converges for some p. If it is convergent, that is the integral exists for some p, then Laplace transformation exists, otherwise it does not exist. So relation between Fourier and Laplace transformation. If f of t is equal to e power minus xt g of t, t greater than 0, 0 t less than 0, then the Fourier transform of f of t is the Laplace transformation of g of t. That is Fourier transformation of f of t, which is equal to Laplace transformation of g of t. We'll see the proof. Given f of t is equal to e power minus xt into g of t, t greater than 0, 0 t less than 0. That is equation number 1. We know that Fourier transformation of f of t is Fourier transformation of f of t, which is equal to f bar of p, which is equal to integral minus infinite to plus infinite e power I pt f of t dt. Right? We are using Fourier transform definition. Instead of x, we are using t, right? So this is equal to, so splitting the integral, so minus infinite to 0 e power I pt f of t dt plus integral 0 to infinite e power I pt f of t dt, which is equal to integral minus infinite to 0 e power I pt. In the first interval, using 1, we are having f of t equal to 0, 0 into dt. In the second interval, integral 0 to infinite e power I pt, f of t is equal to e power minus xt g of t dt, right. So that is equal to integral 0 to infinite e power I pt e power minus xt g of t dt. So grouping the power of e, which is equal to integral 0 to infinite e power ip minus x of t into g of t dt, right. So t is common, take it outside, so you will get e power ip minus x into t. Taking minus outside from the power, so that is equal to integral 0 to infinite minus x in x minus ipt g of t dt. Put x minus ip equal to s, you will get f of Fourier transformation of f of t, which is equal to integral 0 to infinite e power minus st g of t dt. So e power minus st g of t dt is nothing but Laplace transformation of g of t, right? Thanks.